Welcome. Today we're going to talk about flow in closed channels as opposed to open channels. And I'll just explain the difference in a minute. But first, I guess I need to explain to you why this Christmas tree is sitting here. Well, first of all, this is being done in December. I originally did the video for this lab back last summer, but the experiment has changed, and I think changed for the better. And so we've added some digital flow meters, and we've picked up another part of the experiment. So hopefully you'll enjoy the experiment more and you'll get more out of it. But as far as the Christmas tree is concerned, as you know, the site on which I use as the vehicle for this fluid mechanics lab on the open web is also a family history site, and there's some family history sitting right there. This tree is about, it was my grandparents, it was about 60 or 70 years old. So I thought, hey, it's December, you can enjoy it. But in any event, and I'll be using that space over there to explain some of my concepts. So let's begin. I talked first about the difference between open channel flow and closed channel flow. We're going to talk about closed channel flow. Closed channel flow basically is where the fluid passing through some type of conduit, and you see I'm really using very technical language here, it basically fills the conduit. With an open channel flow, it does not. Open channel flow we're going to talk about when we get to the hydraulic jump experiment and the flume. But closed channels are an important part of a great deal of engineering. And that includes a lot of process engineering, such things as refineries, chemical plants, even in some cases, although usually done open channel, sometimes even granular material transport, although, as I said, usually that's an open channel kind of thing. They're important to understand. Designing them properly and configuring them properly and understanding how they operate is an important part of a lot of different types of engineering. Another example, which I have personally been involved in over the years, have been hydraulic systems. So with that in mind, let's proceed. I have an online, I call it a handout. It's actually just a web page which actually explains the theory behind this and gets into some of the more important concepts. And I'm going to go through, basically just go through that. That's all I'm going to do, and I would suggest you read it, because the one thing I'm not going through in this video are the example problems. I've seen over the years students do some, really struggle with the units, particularly the US units. And I want to make it possible to see if we can avoid some mistakes. So I strongly suggest that you would read that and to use the information that's there. I start about Euler's equation. Now, Euler's equation, as I explained in viscosity, assumes that fluids are inviscid. It's a way of predicting fluid flow in an inviscid environment. And we know that inviscid fluids basically only exist in somebody's computer. And so with that in mind, we have to make allowances for that. We're going to see how the allowances are made. But I show right off the bat that inviscid flow in Euler's equation Bernoulli's equation can be derived from Euler's equation. Bernoulli's equation is something we've run into before. You've seen it with, you've seen it in earlier experiments, and we're going to see it again. Bernoulli's equation basically states that the energy at state 1 is equal to the energy at state 2. It's a conservation of energy statement, among other things. And it basically breaks down to 3 components. The first component is energy from an external force field. Usually that means gravity. Now for this experiment, that's the first thing we're going to do is to throw out the gravity term. Now the gravity term is important in these systems, and particularly for you who are in civil engineering. Gravities are obviously with water systems, and of course virtually everything in soil mechanics is done through the gravity-driven flow in a porous medium, i.e. the soil. So gravity systems are important, but they're not going to be what we're going to consider today. And they can, and be advised, they can enter into closed pipe systems. They definitely do. But we're going to get away from that to get to some of the concepts. That's the first thing we're going to do. The second thing is the pressure energy. Pressure there's energy in pressure. And even though with incompressible fluids, that's what we're going to talk about today is compressible fluids. We're going to stick with those. Compressible fluids certainly obey these, but the implementation is a little more complicated. And so the last one is velocity or kinetic energy, the fluid in motion. And so with those three, we basically say that the sum of those energies at state 1 is equal to the sum of the energy at state 2. And with that, we're also going to assume, since it's incompressible, that the two densities are the same. And with that out of the way, we do a little math and we end up with an equation that basically has only pressure and kinetic energy. Now, we have a problem. We know that viscosity creates frictional losses, nullitis losses in fluids. But Bernoulli's equation does not explicitly allow us to consider those. How do we do it? Well, we enter a little called H sub L, a head loss. And by head loss, we're talking about, static head of fluids. And we consider the head loss. And if we insert that into the equation and make a couple of changes. First of all, we do some rearranging, and then we add something else, the continuity of mass flow. In other words, that the mass flow at point 1 is equal to the mass flow at point 2. That is not only an assumption, that is an objective, because basically if you have mass, if that is not true, then you've got a leak, usually. Now, there are times when we do drain fluids off, but for our purposes, we got a leak. We're going to assume we don't have any leaks. The next assumption we're going to make is that the velocity is uniform across the cross-section of the pipe. That's not really accurate either, but particularly in turbulent flow, it's good enough for our purposes. So we make that assumption. We do some other math, and we end up with an expression of what we would anticipate the change of head across, in our case, a flow device or something would be. In this case, we're actually aiming towards flow devices. Well, the change of head is basically the change of pressure across the device divided by the unit weight of the fluid. So we do some more rearranging and math, and we end up with a flow. Basically, we end up with a situation where the flow is a function of the geometry of the system. The head loss we measure, the head difference, and then we all make a decision. The delta H is the head difference, and the H of L is the head loss across the device, because actually you could get a head difference just by from other factors. So what we do at this point, if we can know the head loss and we can measure the head difference, we could estimate the flow from the geometry of the device, from the area ratio. At this point, however, we don't have a good way of differentiating between the two, the head loss and the head difference. At this point, we pull out the last big rabbit in the hat. And that is that we basically say that we just simply dispense with the head loss term and include instead of having an additive term, we convert that to a multiplying term called the coefficient of discharge. The coefficient of discharge, now there are several ways of defining that. It varies from 0, which means there's nothing going through, to 1, which means that there are no head losses at all. And it is and we can, if we know the coefficient of discharge for a certain device, and we know the geometry of it, we know the head difference that the manometer is measuring, we can end up being able to estimate the flow. Conversely, if we know the flow, then we can actually solve for the coefficient of discharge and calibrate the flow device. And traditionally, that's how it's been done. So at this point, we have an equation where we can use the physical characteristics of a flow measuring device to estimate the flow. And for years, that's the way it was done. And it's still a useful exercise because it shows us the effect of how we can actually use these devices in this way, and at the same time take into consideration whatever viscous losses are in the device. Now you say, well, that's all wonderful, but how do we implement that? Well, what we do is we have called classical flow meters. The first one is the simplest, which is a sharp edge orifice. We have 2 of those in our setup. And we take that, we basically measure the head difference across that, as you see in the diagram, and we can use that to if we have a known flow, we can use that to calibrate the device. And if we know the coefficient of discharge, we can use that to estimate the flow. And that's pretty much the quickest and dirtiest of the bunch. There are a lot of losses in sharp-edged orifices, as you might well imagine. They're not very aerodynamic. But they are the simplest and the very common. By the way, as someone who has done this in practice, they can also be used to you can also use that to estimate losses in valves and such things that imitate a sharp-edged orifice in terms of their losses. And I've seen that done over the years. You can also have a flow nozzle, which is basically a sharp-edged orifice with a little bit of a radius on it to cut down the losses. And the coefficients of discharge will be higher for those than they will be for a sharp-edged orifice. The lower the coefficient of discharge, the more losses you're experiencing in the system. And last but not least, we have the Venturi, which is the most efficient of all of these things. It gives a nice gradual neck down to a smaller area where the velocity increases. That's the key to these is the fact that as the area decreases, the velocity increases because the flow is the same and the density of the fluid is the same because it's incompressible. The drawback for the Venturi, so we should always use the Venturi. If we can, we should. In some cases, there's not enough real estate in the pipe to do that. You'll see when we go through the lab that the Venturi takes up quite a bit more. In our flow bench, it doesn't make any difference. In real life, it can. There is nothing in the theory that says that a coefficient of discharge is constant. You will look at tables of such and such a type of orifice or Venturi has such and such a type of coefficient of discharge. Those should be correlated, technically at least, with a Reynolds number. And in fact, that's what you're going to do in the lab. The way this experiment is structured, you will actually take a variety of flows through these orifices, and you will determine the coefficient of discharge at a variety of Reynolds numbers. In other words, your goal is to plot coefficients of discharge on the x-axis, Reynolds numbers on the x-axis against coefficient of discharge on the y-axis. And please don't reverse those. I made mention that these are the traditional flow meters, which they are. There are other types of flow meters. We've got today a wide variety. You've got a digital flow meter. There's paddle wheel, magnetic flow meters, and all kinds of flow meters out there. The old standby for flow meters in terms of non-traditional is the rotometer, which actually goes back over 100 years. And you will be actually comparing one of those to the to the reference flow meter, which in our case is the digital flow meter. And you'll see how accurate or inaccurate it is. It's a very similar process to the one used with pressure gauges, which is covered in another video. So you will be doing that as well. The next thing we want to talk about are so-called minor losses. And I don't know why they're called minor losses, because if you don't design a system properly, they can become very major. What I'm particularly thinking about is things such as valves, T's, elbows, that sort of thing. And if anytime you send the fluid around a corner or through an odd geometry, you're going to get additional losses. And these losses are expressed a little differently. The theory is that, without going into the details, the theory is pretty much the same, except we rearrange some of the math and whatnot. And the reason why we do this is because with valves and whatnot, we don't always have, particularly like valves, like the gate valve that we're going to be testing, we don't normally have a good handle on the internal geometry of it. With a flow meter, the area going in, the area it necks down to. With a gate valve, you may not know that, or any other kind of valve or device. So we basically set up the so-called flow coefficients, the K values, so to speak, where we don't need to know that. The K values can be above 1, and very frequently are for high loss devices. In this experiment, and again, I explained go through the math in some detail. I said that you could actually relate K values to discharge coefficients if you know that internal area. So, in any event, that's those K losses, and they're important. One thing we can also do with the K losses is we can actually, and this kind of slides us into our last our last topic, is we can actually take those and make those to an equivalent length of pipe. And if we do that, and I also explain how to do that at the very end of the handout, how to do this. And if we can do that, we can, if we do that, then we can actually make a valve or whatever, or a corner, into an equivalent length. And basically treat the whole system like a long piece of straight pipe, which makes it a little easier to put things together and figure out how much loss we have from one end of a system to the other. So these minor losses are important. The way we're going to do this is we have a gate valve in the system. We're going to crank it down, say a quarter of the way down, or 3/4 of the way, fully open, 3/4 of the way, halfway open, quarter way open. And we're going to measure for a series of flows. We're going to measure the head loss across those and use those to compute the K values to see how they vary against the flow that's put through them. I might add that again, as is the case before, there are sample calculations which you need to familiarize yourself with. This experiment is carried out in U.S. units. The units would be a lot simpler if they were in SI. I agree with that, but that's just the way this is set up. The last thing we're going to talk about are flow in pipes, which is generally speaking where people start, but this is where we're going to end. Reflective of the fact that in many cases, the way in which we attack subjects from a pedagogical standpoint in engineering is arbitrary to some extent. So with that in mind, we talk about flow in pipes. If you have let's just consider a straight piece of pipe. The straight piece of pipe will have flow through it. That flow can be laminar or it can be turbulent. That flow can be, the walls of that pipe or tubing or whatever can be rough, or they can be smooth, or they can be and roughness, that's not a either or proposition. There are variations in grade of that. There are, that diameter can be small or it can be large. The flow can vary. The question is that we would like to know, particularly, and long pipes can be very long. So the question is, what kind of losses can we expect in pipes, in piping? And we see piping in all types of systems and process plants and hydraulic systems and that sort of thing. So how do we? The classic solution to the problem, and I'm not going to go into all the theory behind it, is the Moody Chart. And the Moody Chart was developed back during World War II. And it basically encapsulated a lot of research that had been done in both theoretical and practical and experimental research into the nature of fluid flow in pipes. And it's a little tricky to use. Let's define some quantities for the Moody Chart that we need to have. The first thing we need to know. Let's look over on the right side. We do that. When we do that, we see a thing called relative roughness, which is equal to, for the Moody Chart I'm using in the handout, is equal to epsilon, which is the roughness or the asperity of the surface, either in feet or meters, or in the chart's case, millimeters, over the diameter of the pipe. It's the ratio of the diameter of the roughness of the asperities to the diameter of the pipe. It can be sometimes you'll see it as epsilon over d. Sometimes you'll see it as d over epsilon. So we're going to use epsilon over d. It's the more traditional way of doing it. But you see it both ways depending on the textbook. Okay, that's the that's one quantity you need to do, and you need to compute that. The second thing you need to know is Reynolds numbers. They're at the bottom on the x-axis. Well, basically that is, of course, when we know how to compute Reynolds numbers. And if you don't remember how to compute Reynolds numbers, or you're not very good at it, then you need to, I've got some help on that too at the bottom. For Reynolds numbers in the very low stages, flow is laminar, and it's very easy to compute the losses. And so up to a point. And then there's a transition period, and some charts have gray shaded. And then there's the turbulent part. We're going to concentrate on the turbulent part. Most flow you get in practical applications is turbulent. If it's laminar, then it's pretty slow. By the way, speaking of laminar flow in closed conduits, human blood runs through our bodies with laminar flow. But but over on the right is a thing called the friction factor. The friction factor, and then we take that and we use that friction factor to determine the head difference or the head loss in a stretch of pipe. So obviously from the Moody chart, you need to know basically this procedure runs like this. First, you determine the relative roughness. Second, you determine the Reynolds number. And using those two, you can determine the head loss using the equation given in the handout. Now, because you use the first two to determine the friction factor, and from the friction factor you determine the head loss. Now, Moody charts have been used as charts for many years. I present a nice correlation which dates from the 70s, where you can actually plug into an equation. If you're using a spreadsheet, it's much easier to do it this way. Much easier to do it this way. And if you're but you just got to make sure you're in turbulent flow when you do it. So you have to compute your Reynolds numbers first. Okay, there is an example that shows you how to actually compute these. In our experimental, we have a stretch of copper tubing, and we've put a digital manometer on it, and we're going to measure using that. We're going to take a digital manometer, and we're going to measure the head loss, which is an expression of the pressure difference between one end of that stretch of pipe and the other. And by knowing the flow that we do, we can actually see, if we could use that, I guess, in theory as a flow meter, and generally speaking, we don't. Generally speaking, we let the traditional flow meters or your newer flow meters be a flow meter. But what we have is a digital flow meter, and we're going to see if the losses that we estimate in the theory line up with the losses that we get in the lab. That's what we're going to do. And so we're able to, if we know the flow going through, and actually I present the equations for both Reynolds number and the head loss in terms of flow as opposed to velocity, which which kind of eliminates a step in as far as the tube diameter is concerned. It's just something a little convenient to prevent getting tripped up doing that. The only thing you got to be careful about is what units. The units presented in the handout are feet, and is feet, and pounds, and seconds, and all that. So therefore, your flow needs to be in cubic feet per second, whereas the flow meter reads it in gallons per minute. So you need to keep that in mind as you look at the data either on the video or in the lab. So that is your task for the piping losses. Piping losses, again, are very important, and they need to be taken seriously in the design of process facilities and in terms of any device that uses fluids to motivate. And actually, that includes most of them in one way or another. So in any event, that is, in a nutshell, the theory behind this lab. So let's go to the lab and see what's going on. This is the flow bench setup, the pump for the flow bench, and it's kind of hard to see, but it's at the bottom right-hand corner of the video screen. And then the controls are at the top right corner. The flow goes in what would be a counterclockwise motion out on the far side of the table, then come around and comes back on the near side of the table. And I'm going to give you a tour, more detailed tour of it, and to explain exactly what is going to happen. We'll start here with the pump itself, and above it is the controls. There's a little knob you see, and that knob controls the flow of the system. However, you just can't dial in a flow with this system. What you have to do is to use this, which is your digital flow meter, to measure the flow. And you basically fiddle with the knob until you get the flow you want, or close to it. You never can really hit it exactly. The first thing that comes up are your conventional flow meters, and this is the first one, which is the this particular one is the orifice flow meter number 1. And it is measured, the head across it, by this, which is digital manometer. The second one is the flow nozzle, which is measured by this digital manometer here. The third one is the venturi, which is here, and it's going to be measured by the digital manometer here. This stretch of the flow system has a dual function to it. One of them is this rotometer, which I discuss in the lecture. The other one is another digital flow meter, which you see down there, and that is to measure the head loss between those two ports. Well, you'll be given the distance between those two ports as far as the flow distance. In other words, from the first one on the left up to the rotometer, across, back down to the right. You'll be given the diameter of that pipe, and you'll compare the flow losses. You'll get a K values for those, and then you'll compute the equivalent length of that flow to see what difference all those elbows and that rotometer have in the flow. You'll be able to, this is a little different from the way we've done it in the past, and it's a little different from the way I described in the lecture. We used a gate valve in the past, but now all you have to do is to, at the same time while you're collecting data on the other flow, on the other traditional flow meters, you'll also be collecting data on this one. So you basically collect this data and the data for the flow meters in one shot. You'll be able to make those calculations from there. It's a little hard to see in places, but here is the beginning, the copper tubing, and we'll just go right past where it goes behind the rotometer. And this copper tubing, the length is given in the procedure, and the diameter and all the dimensions that you'll need. And the head loss between the port you saw just moments ago and this one right here is measured by this digital flow meter. And we'll be able to do a Moody Chart correlation based upon that. This last is the second orifice. And we measure the head loss not by a digital manometer, but by a standard conventional manometer. And the reason why we've kept this in the experiment is to show you what exactly one looks like and how you read it, and also what it really means to say what is head difference between 2 points. That's not always an easy concept to grasp, and it's not always easy to wonder why we do it this way, but this standard manometer, I think, will answer those questions for you. This last is the receiver tank where the water goes back. I think I explained the need for a receiver tank when we were talking about the pressure gauge testers, and I won't go through that again. But that is the receiver tank. The experiment itself will be divided into 2 different parts. The first part will be, we're going to look at the conventional flow meters on the far side of the table, and the rotometer and the minor loss over here on the near side of the table. And that includes, of course, the second orifice right in front of you. The second part of the experiment will be the Moody chart through that copper tubing. And what I'm going to do is I'm going to present you data, give you a flow, and then give you the data you need after that flow in a very particular order, and you just simply write that data down and analyze it. The last is a Moody Chart test. We have this piece of copper tubing, that's in the lower part. The upper part, you'll see what it's good for in a second. And it goes along across the breadth of the flow bench, and it reaches a point where we'll have a digital manometer for that. The digital manometer will record the head loss, again in inches of water, from one end of this to the other, or at least between the two taps. And all the dimensions will be given to you. This is the one place, and we'll find out for different flows what the loss is in this piece of pipe, and you'll be able to correlate that and see how well it matches the Moody chart. There is one important thing to do. For the first two experiments, we have these three valves. Valve 7 is open, and valves 4 and 5 are closed for the flow meters and the gate valve. For the Moody chart, the pipe losses, the 7 is closed and 4 or 5 are open. And that concludes the experiment. So, as always, thanks for watching, and God bless.